If you've watched all 31 videos in this probability course so far, you'll be left with the strong impression that probability theory is a subfield of analysis. In particular, it's just measure theory. That is a false impression based on how much time we've had to spend building up the background to move forward with probability theory. But now we're finally here. Today we will start with a topic that is purely probability and definitely differentiates the subject from analysis: conditioning and independence. We're only going to start very briefly with the notion of conditional probability. We'll come back to it later in much greater detail. Given a probability space and an event in that probability space that has positive probability, we can construct a new measure called the conditional probability relative to that event B. It's defined on the same sigma field, and it is defined as follows. The probability of A given B is the probability of A intersect B divided by the probability of B. It's not at all hard to check that this is a genuine probability measure. In fact, doing so was essentially on your first homework assignment. What does it mean? Well, our probability space models some experiment, and in this experiment, we're looking at the likelihood of different events occurring. Those likelihoods are determined by certain experimental setups. As we conduct the experiment, we might get new information that a certain event B is no longer in question. It has occurred. And so now we want to know what are the probabilities of other events given that information. Some of them might not be affected, others might be affected greatly. This conditional probability is a model for that. For all events, it tells us what is their probability given that we now know that the event B occurred. Let's look at our favorite example in terms of tossing a coin. If we toss a fair coin twice, our standard model is the sample space consisting of these four outcomes: heads, 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 tails, tails, heads, and tails, tails. Since it's finite, there's no technical obstruction to taking the sigma field to be all subsets, and as usual, we have the uniform probability measure. Any one of those four outcomes is equally likely. Now let's look at a particular conditional probability. What is the probability that the second toss is heads, given that the first toss was heads? Does the first toss being heads give us any information about how likely it is for the second one to be heads? If you've ever gambled in a casino, you will have a gut feeling that the answer to this is yes, absolutely. But you might not agree which way it goes. You might believe that there are winning streaks, and so this makes the second heads more likely. You might believe, on the contrary, that having more heads in a row is less and less likely, and so if I've had a bunch of heads in a row, the next toss is less likely to be heads. Let's actually do the calculation. By definition, this is the probability of the intersection of the two events divided by the probability of the second event. Well, what is the first event? The event that the second toss is heads consists of these two outcomes. And the second event that the first toss was heads consists of these two outcomes. Now, that intersection in the numerator has just one outcome in it, heads, heads. So this is the probability of the singleton, heads, heads, divided by the probability of the two outcome event, heads, 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 tails. The top has probability 1/4, the bottom has probability 1/2, and so we get 1/2 as the conditional probability that the second toss is heads, given that the first was heads. Now, notice that that 1/2 is exactly the same as the probability that the second toss is heads, full stop. After all, this event is just the two outcome event, heads, heads, tails, heads. So what we see here is that the probability of A given B, in this case, where this is the event A and this is the event B, is just the same as the probability of the event A. The likelihood that A occurs didn't change when we were given information that B occurred. Using the definition that this is the probability of A intersect B divided by the probability of B, we can rewrite this outcome as the probability of A intersect B equals the probability of A times the probability of B. That's a nice way to write it that doesn't actually rely on the event B having positive probability. And so we see that in this case, these two events are statistically independent. The likelihood of one of them occurring does not change when given information about the other. So that's our formal definition. Two events in a probability space are called statistically independent if the probability of their intersection is the product of their probabilities. This makes sense even if one or both of them have probability 0. But notice that in the case where the probability of B is positive, we can then divide by the probability of B and see that this is equivalent to the conditional probability of A given B is the same as the probability of A. Similarly, if the probability of A is non-zero, then this is equivalent to the conditional probability of B given A being the same as just the probability of B. There's a nice symmetry here. If A and B are independent, then B and A are independent. Now, more generally, we'll talk about classes of events being independent. If I have two sets of events, C1 and C2, in the sigma field, we call them independent if, given any event from the first class and any event from the second class, those two are independent. It will be useful and customary to apply this usually when those classes are sigma fields, although that won't always be the case a priori. We will soon see that we can usually boost independence from classes to sigma fields under reasonable conditions. We could make the definition just for sigma fields of events if we note that we can recover the original definition by saying that two events, A1 and A2, are independent if and only if the sigma fields they generate are independent. That might sound like a stronger property, but let's note that for a single event, the sigma field that it generates has four elements: the empty set, the event itself, its complement, and the entire space. That is, at most, four elements. If A is either the whole space or the empty set, this will only have two elements. The observation from that is that if A and B are independent in this sense, then they're also independent in the sense that their sigma fields are independent. And why is that? Well, we just need to check that all four elements here on both sides for A and B satisfy the independence criterion. So let's just check that. Let's hold A fixed and vary elements of the sigma field generated by B. The probability of A intersect the whole sample space, well, A intersect the whole sample space is just A, so that's the probability of A, which is the same as the probability of A times 1, which is the probability of A times the probability of the whole sample space. Therefore, the sample space is always independent from everything. Now, our assumption was that A and B are independent. What about A and B complement? Well, we can just draw a little picture here. If this is B and this is A, then A intersect B complement is this over here, which is the same thing as A minus the intersection of A and B. So that's the same as the probability of A minus A intersect B. And so since P is finitely additive, this is the same as the probability of A minus the probability of A intersect B. Our assumption is that A and B are independent as events, and so the probability of A intersect B is the probability of A times the probability of B. And so this factors as the probability of A times 1 minus the probability of B, which is the same thing as the probability of A times the probability of B complement. And therefore, if A and B are independent, so are A and B complement. In particular, putting these two together shows us that A and the empty set are independent, since the empty set is the complement of the whole space. And now we can run through the same holding b fixed and varying a if we like, but we'll get the same result. So independence has nice functorial properties transferring to sigma fields, at least the sigma field generated by a single event. In a few minutes, we'll see how we can generalize this to sigma fields generated by larger classes under the right conditions. But first, let's talk about independence of more than two events or classes. What should it mean for three events, A, B, and C, to be independent? One possibility is to just declare that it means pairwise independence, that any two of them are independent from each other using the notion we already developed. So let's look at an example of pairwise independence. Let's take two fair coin tosses again and consider the following three events. The first event is that the first toss is ahead, like before. The event B is that the second toss is ahead. And the third event, C, is that the two tosses are different from each other. So we can just write down in terms of the sample space that we have what those events are. Each of them have exactly two elements. That means that each of them has probability 1/2, and therefore the product of the probability of any two of them is 1/4. Now we just need to check, what are those intersections? Well, A intersect B is the event that the first and second tosses are both heads. So that's only one event. That's the probability of heads, which we know is 1/4, which matches this. And that means those two are independent. How about A intersect C? That's the event that the first toss is heads and the two tosses don't agree, which means that the second toss is tails. And so this is the probability of the single event heads-tails, which again is 1/4. Good. And B intersect C is the event that the second toss is heads and the two don't agree, therefore the first is tails. So this is the probability of the singleton tails-heads, which is also 1/4. And we see that these three events, A, B, and C, are pairwise independent. But if independence is going to have any actual philosophical meaning, these three events cannot be considered independent. Because if I know that A and B both occur, then I know with absolute certainty that C does not. A and B together mean heads, which means that C cannot happen. Therefore, those three events should not be considered independent. So this pairwise independence is not going to be the right notion of independence that we want. Now, if we want to use the set theory symbols that we've been working with so far, this implication that A and B implies the negation of C, we could write simply as the intersection of A and B is contained in C complement. In other words, A intersect B intersect C is the empty set, which means that it has probability 0. Now, on the other hand, furthering the pattern of what we saw statistical independence means, if we take the product of the probabilities of all three of those events, that's 1/8, which is not 0. And so that's one numerical way that we could define independence that would show us why this set of three events is pairwise independent, but not independent. But we need to be careful. We might just want to say independence of three events means that the probability of their intersection is the product of their probabilities. But that is weaker than what we had before. That does not imply pairwise independence. For example, suppose that we just take C to be the empty set, and A and B be any two events. Well then, this is 0, and the intersection here is empty, and therefore this is also 0, so we do get agreement of this triple product. But we could certainly arrange it so that A and B are not independent from each other, so that the probability of A intersect B is not probability of A times probability of B. For example, we could take A equal to B to be an event that has probability neither 0 nor 1, and then this would show that the triple product does not imply pairwise independence. If you'd like, you can think up more interesting counterexamples as well, where none of the three are the empty set. Those actually play an interesting role in hashing problems in computer science, but that's outside the scope of this course. So we want a definition of independence for multiple events that is robust. And in fact, it makes sense to flip the script here and define independence for classes of events, specializing to individual events afterward. So suppose I have n classes of events C1 through Cn in a sigma field, we call them independent if, for any subset of the indices 1 through n, that's what this notation means, by the way, square brackets n is the set from 1 up to n, the probability of the intersection of events ai taken with indices in the set capital I is the product of the probabilities of those events for any choices of events ai in class Ci. That's a bit of a mouthful. Let's look at an example with n equal to 3. With n equal to 3, let's look at all subsets of the set 1, 2, 3. There are, of course, 8 of them. If we take the empty set, then the statement here is vacuous. If we take the 3 one-element sets, then those are just the statements that the probability of ai is equal to the probability of ai, which is automatic, so we never need to consider that. How about the 2-element sets? Those are the probability of ai intersect aj, where I is not equal to j. And the statement is that those all have to be the probability of ai times the probability of aj in those cases. In other words, the 2-element sets give us pairwise independence. And then the 1 3-element set gives us that the probability of a1, a2, a3 intersected is equal to the probability of a1 times the probability of a2 times the probability of a3. So this condition here gives us all of the double, triple, quadruple, etc. comparisons that we need together to mean independence. Now, I want to show you what's more or less a notational trick, but that makes this a little easier to digest at the level of classes of events, which is to say, from this definition, if I have a finite set of classes that are independent, then I can throw in the whole sample space to each class, and those will also be independent. The proof of that is just like we saw on the previous slide, because the whole sample space is independent from everything. But having that in place makes the notation a whole lot easier here. Because, for example, if I had n equal to 5, here's one of the 3-element subsets we need to consider. A1 intersect A3 intersect A4. But I could just write that as A1 intersect the whole sample space, intersect A3, intersect A4, intersect the whole sample space. And indeed, the probability of A1 intersect A3 intersect A4, which for independence to hold is supposed to equal the probability of A1 times the probability of A3 times the probability of A4, is also equal to the probability of A1 times the probability of the whole sample space times the probability of A3 times the probability of A4 times the probability of the whole sample space. And so allowing the events AI to include elements of the class Ci and the whole sample space, in other words, by including the sample space in Ci, we can restate independence as just requiring that if I have classes C1 through Cn that, without loss of generality now, we'll assume include the whole sample space, they are independent if and only if the probability of the intersection of A1 through An is the product of 1 through n, the probability of Ai, for all choices of Ai in Ci, because Ci includes the whole sample space. That's a compelling reason to always, without loss of generality, assume that our classes include the whole sample space. Now, like before, if we want to talk about independence of n events, we would say that n events are independent if and only if the sigma fields that each of those n singleton events generate are independent. Those sigma fields each include the whole sample space by definition, and so that fits this definition right here. But it does, of course, include all of these conditions automatically. Now, that might leave you with the impression that independence of classes of events implies independence of the sigma fields they generate. But that is not true in general. It is true if the classes are singletons, as we saw on the first slide. But if I have arbitrary collections C1 and C2 of events that are independent from each other, it does not follow that the sigma fields, sigma of C1 and sigma of C2, are independent. And you're going to be looking for such a counterexample on your homework. However, it does imply it if those classes of events are closed under intersection. Let's give some standard notation for that. Given a sigma field F, a class of events in F is called a pi system if it is closed under finite intersection. Simply meaning, given any two events A and B in the class, their intersection is in the class. This notation pi system was introduced by Dynkin and is 1/2 of Dynkin's pi lambda theorem, which we have avoided so far and will continue to avoid. However, his multiplicative systems theorem is a functional version of it, and we're going to use it in a moment to prove the following theorem. Given any independent pi systems, that is, given a finite collection of classes of events, each of which is closed under finite intersection, then indeed the sigma fields they generate are independent. The case we've seen so far, where each of the classes consists of a single element, satisfy this mold. A single element set is of course closed under finite intersection, but this holds for any classes here, be they finite or infinite classes of events. The proof of this relies on another nice application of Dynkin's multiplicative systems theorem. And here's the critical lemma. If I have a pi system in a sigma field, and if I have two probability measures on that sigma field that agree on that pi system, then they automatically agree on the whole sigma field generated by that pi system. Let's prove this. Our assumption is that C is a pi system. It's closed under finite intersection. We're going to write that in functional terms. Let's let M be the set of all indicator functions of events in the pi system C. Now that is a subset of the bounded measurable functions, measurable with respect to the sigma field F where all of these are taken from. Moreover, if I take two such indicator functions that are both in M, and I take their product, we know that the product of two indicator functions is the indicator function of the intersection. And since this class C is a pi system, since it's closed under intersection, that means that this is back in M. So what have we shown? We've seen that M is a multiplicative system. Indeed, this is the standard connection between pi systems and multiplicative systems. Now, let's define H to be the set of all bounded measurable functions with the property that we want, that the integral of f d mu is equal to the integral of f d nu. In particular, if f is the indicator function of an element of C, then this property holds by assumption. In order to apply Dynkin's multiplicative systems theorem, we need to verify a few things. We need to verify that 1 is in H. That is to say that 1 is a bounded function, of course, that integrates to the same thing against mu and nu. But of course, the integral of 1 against mu and nu are both 1 because mu and nu are probability measures, and so indeed 1 is in H. We need to see that H is a subspace, but that follows immediately from the fact that the integral is a linear functional. If I take a linear combination of functions in H, then the integral of that linear combination is the same linear combination of the integrals on both sides, and so the agreement of the integrals of the individual functions will give us the agreement of the integrals of the linear combinations. We need to see that H is closed under bounded convergence. And that follows immediately from the bounded convergence theorem, or if you like, the dominated convergence theorem with a constant as the dominating function. Because if I have a sequence fn of functions that are bounded above by some constant m, then if fn converges almost surely to f, the integral of fn converges to the integral of f against either measure, mu or nu, by the dominated convergence theorem, since the constant m is integrable with respect to a probability measure. And therefore, since I get agreement of the sequences integral of fn d mu and integral of fn d mu by assumption, since fn is in H, the same property holds for the limit, and that means that H is closed under bounded convergence. And finally, as we already said, M is contained in H. And that's just because the integral of the indicator function of any element of C against mu is equal to mu of B, which by assumption, since B is in C, is the same as the measure nu of B, and that can be written as the integral of the indicator of B d nu. And that shows us that 1b is in H. Therefore, by Dynkin's theorem, we conclude that the space of all bounded sigma of M measurable functions is contained in H. Now, certainly among those are the indicator functions of events A in that sigma field generated by M. But what is the sigma field generated by M? That's the sigma field generated by all events of the form the preimage of F on E, where E is any Borel set over the reals, and F is any function in M. In particular, if we take that function to be the indicator of B for any B in the class C, and if we take E to be the singleton 1, then F inverse of E is indicator of B preimage of 1, which is B. And so this contains the sigma field generated by all events B that are in C. And so we see that the indicator function of any event in the sigma field generated by C is in H, which is exactly to say that nu of A is equal to mu of A, which is what we wanted to show. All right, now let's use this lemma to prove the theorem that I mentioned. If I have any finite collection of classes of events that are independent pi systems, each of them is individually closed under finite intersection, then the sigma fields they generate are also independent. Now, we're going to do this in the case n equals 2. The general case follows by induction. So let's fix some subset B in the class C2. Now, if that event has probability 0, then the probability of the intersection of A and B, well, A intersect B is contained in B, so that's less than or equal to the probability of B, which is 0. But of course, that's also equal to the probability of A times the probability of B, since the probability of B is 0. And that holds true for any event A in F, and so in particular, any A in the sigma field generated by C1. So for any probability 0 event B in C2, it is independent from the whole sigma field generated by C1. We're going to show that same property holds for non-zero probability events B. If B does not have probability 0, then we can condition on it. The probability measure conditioned on B is another probability measure on F, and moreover, that probability measure is equal to the original probability measure B on C1. In other words, our assumption is that the probability of A is equal to the probability of A given B for all A in C1, and that follows from the assumption that C1 and C2 are independent. So here I have two probability measures that agree on C1. C1 is by assumption a pi system, and so by the lemma, it follows that those two probability measures, the conditional probability and the original probability, agree not only on C1, but on the sigma field generated by C1. That is to say, we have established that the probability of A intersect B is equal to the probability of A times the probability of B for all A in the sigma field generated by C1 and for any B in C2. Now, in order to prove the theorem in the case n equals 2, we need to upgrade this to B in the sigma field generated by C2. And in order to do that, we simply have to run through this argument one more time, this time holding the event A fixed. And the argument will be exactly the same. And so you can see that if we were doing this with a general n, we don't even really need induction, so to speak. We just need to keep doing it over and over n times. It's exactly the same argument, but I guess that's what induction actually means. I'm going to call this proved. This kind of extension from pi systems to sigma fields is definitely going to be useful to us going forward, especially in the next lecture. But before we get there, now let's talk about independence of infinitely many classes of events. We simply define that by finite subset. If I have any collection of subsets of a sigma field, we'll call that collection independent if and only if any finite subset of those collections is independent in the sense that we've just given. So one consequence of that, a simple exercise using the continuity of probability measures, is that if I have a sequence of events, a countable sequence, that are independent, then the probability of that countably infinite intersection is the countably infinite product of the probabilities of the events, where that is defined to be the limit as, say, capital M goes to infinity of the product, n equal 1 up to m, of the probability of an. And that exercise is on your homework. Keeping that consequence of independence in mind, we're now going to finally prove the second half of the Borel-Cantelli lemma. Remember, the first part of the Borel-Cantelli lemma said that if I have a sequence of events whose probabilities form a summable sequence, then the probability that infinitely many of those events occur is 0. The partial converse of that, part 2 of the Borel-Cantelli lemma, is if I have a sequence of independent events whose probabilities are not summable, then with probability 1, infinitely many of those events do occur. Before we prove that, let's look at the example that we gave once before, now having the formal statement here. Suppose that I have a sequence of Bernoulli random variables with some probabilities Pn. For example, Pn equal to 1 over n that form a non-summable sequence. If the events xn equal 1 are all independent, then the Borel-Cantelli lemma, part 2, tells us that xn will equal 1 for infinitely many n, with probability 1. For example, if I toss an infinite sequence of biased coins, I hand you the first coin, which has probability 1/2 of coming up heads. You toss it and record the result. Then I hand you a new coin, which has probability 1/3 of coming up heads. You toss it and record the result. Then I hand you a new coin, which has probability 1/4 of coming up heads. You toss it and record the result. And at the end of a very long day, you look at the sequence of tosses. Then with probability 1, you will see infinitely many heads in that sequence, even though the probability of heads was shrinking to 0 as the tosses went on. That's the power of the Borel-Cantelli lemma. And we'll conclude this lecture by proving it. Let's just recall this nice formulation for the set of outcomes that occur in infinitely many of the ANs. We take the union past some point k of all of the ANs. In other words, for fixed k, this is the set of outcomes that occur somewhere after time k, and we take the intersection of all of those. So this is the collection of outcomes that keep coming back over and over in the tail of this sequence of events. It's the set of outcomes that occur in infinitely many of the outcomes. Now, note that this union here, which I'll call UK, is a decreasing sequence. As k increases, this is a union of fewer and fewer sets, and so it is a decreasing sequence of sets, and therefore, by the continuity of measures, the probability of this set, which is the set where an occurs infinitely often, is the limit, as k goes to infinity, of the probability of that UK, the probability of the union over n bigger than or equal to k of an. Now I'm going to be sneaky and write that inside the limit as 1 minus the probability of the complement, which is the intersection of the complements. And of course, I can pass the limit through the 1, so that's 1 minus the limit as k goes to infinity of the probability of that intersection of complements. Now let's consider fixed k. that probability of the intersection n going from k up to infinity of an complement, since the an's are independent, and therefore, as we've now seen, the an complements are independent, this is the infinite product, n going from k up to infinity, of the probability of an complement, which is the infinite product, n going from k up to infinity, of 1 minus the probability of an. How do we handle an infinite product like that? We have many more tools for handling infinite sums. Well, let's turn this into a sum by taking the logarithm. And the nice part here is that we don't really have to take the logarithm because of a nice calculus inequality. Let's call this probability here Pn, which is a number between 0 and 1. So that's a product of 1 minus Pn. And I just want to note that 1 minus Pn is a non-negative number, but it's also bounded above by e to the minus Pn. That's a simple calculus exercise. Consider the function f at p equals e to the minus p plus p minus 1 on the unit interval. Notice that f at 0 is equal to 0, and calculate that this differentiable function has derivative equal to minus e to the minus p plus 1, which is greater than or equal to 0 on the unit interval, because e to the minus p is less than or equal to 1 there. Therefore, this is a non-decreasing function which starts at 0, and therefore it's positive on the unit interval, which is exactly to say this. And so therefore, this product, as you can easily work out using the limit definition, will be less than or equal to the product n going from k up to infinity of e to the minus Pn. Well, let's write out what that means as a limit. That is the limit as capital M goes to infinity of the product n going from k up to capital M of e to the minus Pn. And now by properties of exponentials, this is the limit as m goes to infinity of e to the minus sum n going from k up to capital M of Pn. Now, for any fixed k, this sum goes to infinity because of our assumption that the sum of the Pn's is infinite. If there were some tail of this sum that was finite, then the whole sum would be finite. So this tends to minus infinity. Therefore, by continuity of exponentials, this tends to 0. In fact, for any fixed k, this is equal to 0 for any fixed k. And so we therefore have that this limit is a limit of a constant sequence. This is 1 minus 0, which is 1, which concludes our proof of the Borel-Cantelli Lemma, part 2. We'll put the two Borel-Cantelli Lemma parts together into a single 0-1 law shortly, and study why it is that the outcomes have to be either 0 or 1. But before we get there, in the next lecture, we're going to now talk about independence of random variables.